Hello, thank you for your interest in our project, entitled Investigate the Use of Discrete Patterned Roughness for Turbulent Transition Control in Hypersonic Boundary Layer. This project is focused on improving the understanding of boundary layer transition in order to extend the range of hypersonic vehicles. This work has been funded by a Phase 2 SBIR from the Navy. I would also like to acknowledge our academic partners, Purdue University. Before I talk about our project, I would like to give a quick overview of Spectral Energies. The company was started in Dayton, Ohio in 2006 as a laser-based combustion and flow diagnostic company. In the nearly 20-year history of Spectral Energies, we have grown to have about 35 direct employees and 35 associates that work closely with the company. We have expanded from our roots as a diagnostic company into many different areas. Some of the key areas we are heavily focusing on include developing hypersonic technology, developing next-generation directed energy solutions, developing alternative position, navigation and timing, developing advanced propulsion concepts like rotation detonation engines, developing and selling custom lasers, and other R&D projects. Our expertise in hypersonics, material science, modeling and simulation, and experimental validation has led us to developing new models that will be relevant to future material development. Our project is funded via the Navy SBIR topic N68335-24-C-0133, titled Investigate the Use of Discrete Patterned Roughness for Turbulent Transition Control in a Hypersonic Boundary Layer. The primary objective of this research is to model, investigate, and understand the influence of rough surface conditions resulting from manufacturing processes, as well as wear and ablation during hypersonic flight, on turbulent transition. A secondary goal is to utilize discrete surface roughness patterns to control or delay this turbulent transition, ultimately achieving drag reduction and minimizing surface heating. The focus of this study is particularly relevant for hypersonic applications, especially in the context of weapon systems. There is a growing recognition that discrete patterned roughness has shown promise in suppressing boundary layer transition on hydrodynamically smooth hypersonic lift-generating configurations affected by crossflow. However, actual vehicles often exhibit roughness from various sources, including manufacturing imperfections and material degradation over time. To comprehensively understand the effects of surface roughness on hypersonic flight vehicles, the research will employ computational fluid dynamics and wind tunnel experiments. Additionally, scaling laws will be developed to predict the implications of surface roughness on full-scale vehicles based on insights gained from lab-scale testing. Understanding the impact of surface roughness from manufacturing and ablation processes on the flow over hypersonic vehicles is critical. There is potential to design patterned surface roughness to control and delay boundary layer transition, which could significantly influence performance. Notably, introducing surface roughness might delay the transition to turbulent flow, resulting in drag reductions of up to 20%. Such reductions could, in turn, enhance the range of hypersonic vehicles by approximately 11%. SE is currently focused on developing both experimental and computational tools to better understand how surface roughness affects airflow over hypersonic vehicles. The research involves observing various flow features that play a crucial role in influencing the overall performance of these vehicles. Through this work, SE aims to gain deeper insights into the complex interactions between the vehicle's surface characteristics and the aerodynamic forces at play during hypersonic flight. The SE team has conducted simulations of realistic roughness conditions, drawing insights from 1950s flight test articles to identify critical instability modes. We developed patterned roughness aimed at mitigating the most unstable modes, with initial simulations and experiments indicating promise in delaying turbulent transition. Moving forward, the team plans to select a more relevant flight vehicle and investigate the natural roughness patterns to evaluate their effects. Additionally, we will develop a methodology for scaling the effects of roughness from laboratory conditions to full-scale applications and assess its impact on range. Finally, the team aims to create techniques for integrating these roughness patterns into flight vehicles. Our product will offer many benefits to the Navy and DoD. 3 major benefits of our work include increased range, reduced testing costs, and better physical understanding of hypersonic boundary layer transition. Delaying or eliminating turbulent boundary layer transition can significantly reduce drag by up to 20%, potentially leading to an 11% increase in the range of flight vehicles. Additionally, SE is working on developing scaling laws that enable measurements at lower hypersonic speeds and laboratory scales to be related to impacts at higher speeds and on full-scale vehicles. This advancement aims to decrease the number of full-scale tests required, streamline the design cycle, and lower the costs associated with flight testing. Furthermore, both experimental and simulated results will enhance our understanding of hypersonic boundary layer transition, ultimately contributing to improved flight vehicle design. SE is working on a comprehensive transition plan focused on enhancing modeling and experimental capabilities. This includes obtaining realistic geometries and roughness patterns, as well as identifying essential partners in the field, such as prime contractors involved in hypersonics. The plan involves integrating these roughness patterns into hypersonic flight test vehicles and demonstrating the benefits, ensuring that any drag reduction achieved surpasses the additional weight and complexity introduced. Additionally, SE is actively seeking sponsors to support the integration of this innovative technology into a flight vehicle. The goal is to conduct flight tests by fiscal year 2026, marking a significant step in advancing hypersonic research and development. SE's product will fit into a few markets. The most obvious market is the hypersonic defense market. Organizations in this field are focused on developing next-generation hypersonic systems to stay ahead of our near peers. This technology could be applied to both future reusable systems as well as missile systems. Extending the range of either of these systems may be crucial. In addition, some organizations are already looking into developing commercial hypersonic transport vehicles. Our technology could help them develop aircraft with lower operational costs. The business model focuses on leveraging research to develop a range of innovative products and services. A key component is the creation of a database that details the effects of surface roughness on vehicle performance, including metrics such as range, endurance, and surface heating. This database will serve as the foundation for developing predictive models that can analyze the impact of roughness on various vehicles. Additionally, the business aims to utilize its tools to generate custom-optimized roughness patterns tailored specifically for individual vehicles, enhancing their performance and efficiency. Thank you for your attention. If you are interested in learning more about our surface roughness project or spectral energies, please reach out to Dr. Sivaram Gogineni or Dr. Christopher Rusher. Their contact information is listed on this slide.